This talk is called, officially called 8 Akka Anti Patterns You'd Better Be Aware Of, but unofficially I call it How to Shoot Yourself in the Foot with Akka. The reason and how I got to this talk is seeing in the field out there at clients what can go wrong. There's this nice quote from Neil Gaiman: tools, of course, can be the subtlest of traps. And so this isn't really a talk about best practices as much as it is a talk about really what you should avoid doing, and then circling back into what you could be doing. There isn't really much of a one big best practice for each situation. There's a few recommendations, and the reason is simply that Akka is not a framework. Akka is a toolkit, and like a toolbox, you can use tools to do various things, and sometimes you use the wrong tool or you use the right tool but in the wrong way. And yeah, this talk is really about that and my experience in seeing Akka in production. So what I'm doing, my name is Manuel Bernhard. What I'm doing is helping clients, companies getting started with Reactive, and that is to say, oftentimes it's a lot of first unlearning rather than learning new things, okay? Because what happens is you have a deep heritage in terms of imperative, mutable, synchronous thinking. And what we need to transition to is this kind of functional, immutable, asynchronous design and thinking. And there is basically two things I'm doing is, well, helping getting started. That's nice. Then people call me in before they get started or when they're just getting started. But then there is also these cases where they're already there and they've moved to production, but now it doesn't work at all. And that is sort of where I'm getting most of the input for this talk from. I'm also a training partner of Lightband. I'm mostly focusing on Akka cluster, like the advanced Akka training these days, or let's say I didn't really choose to focus, it's just I get a lot of requests. 2017 is the year of Akka cluster for some reason for me. I think, yeah, I can really see from my perspective that there is an uptake in this space. I also wrote a book called Reactive Web Applications. That's the book I would have liked to have for myself when I started with this, trying to figure out how it all fits together. So it's how do you build reactive web applications with Play, Akka, reactive streams. The examples in the book are in Scala, but you don't need to be a Scala crack to get started using it. So it's also introducing the functional programming concepts that you need. So enough about myself. Let's move on. So who is using Akka in production here? Or planning, yeah? And who is or not yet in production, but is about to? Quite a few as well, a few. So yeah, so brace yourselves. I mean, I hope that everything works nicely for you. Maybe you can learn a few things here in terms of traps you could avoid, maybe. And the way this talk is going to go is just I'm going to move through a few anti-patterns with a quote in front of each of them. So let's start with the first one. That's the 28th US president who said that, Woodrow Wilson. If you want to make enemies, try to change something. That brings us to our first anti-pattern, global mutable state. So actors, the actor model, one very important thing here is that it's okay to have mutable state. I think there is quite a bit of throning going on sometimes when you say I have a mutable state, I have a var, I have a mutable map. But inside of an actor, that's okay. That's actually one of the few places where it's perfectly okay to have mutable state inside of the actor, so long as you don't lose control over that state. So long as the actor retains control over sharing that state to others and never really loses control over who can change and mutate that state. That's pretty important. So how can it happen that you would lose control over your state? So for example, you can have a mutable map and you send out a message, but in the message you reference that mutable map. Suddenly that reference to this mutable data structure is out there, and someone else could potentially change it. That's one thing. Another thing that I see very, very often is closing over mutable state in asynchronous calls. That's happening when you call using futures inside actors. For example, making a call to a web service and then changing the state in return. And we're going to come back to that in just a bit. And then the third thing I'm also seeing quite often is you have an actor that has a constructor, and then people put maps or configuration parameters inside of the constructor. It's okay to have configuration parameters in the constructor as long as they're not changing. But if you pass mutable state inside of the constructor and then change it after the fact, that's also not ideal. And I think in order to understand why that is not so good, we first have to look a little bit under the hood at how Akka is working in regards to threads, because threads isn't something you should be too concerned about when you're building actor systems. So here is my very nice drawing. So these things there on the side are threads in that box. There aren't that many. So if you're in an evented server, you shouldn't have that many threads. You should have like about twice the amount of cores that you have, more or less, depending on your system, of course. And then in the middle, you have this diamond-shaped thing, which is called a dispatcher. And that's doing all the work and heavy lifting of assigning threads to actors, or rather to actors that are processing messages. So what happens is we will have the dispatcher giving a thread to an actor for the duration of a few messages. By default, that's 5. And then this actor can process these 5 messages, or you can configure this batch size, actually. And then it's moving the thread to the next actor and to the next one, etc. Or you may have another thread that is given to the first actor to do more of their work. So what that means is that you don't have any say in the default, with the default dispatcher. You don't get to choose which thread is going to be given to which actor. It's something you shouldn't care about. So in other words, using thread locals in actors is a very, very bad idea. I've seen that happen, but it's something you shouldn't do. More generally speaking, this model of execution is really performant. There is but by default, the executor in place is the fork join dispatcher. And there is another one called the affinity pool. So circling back to yesterday's keynote where we talked about scales and locality, there is one that's a bit more performant for high-performance systems than the fork join dispatcher is also in Akka now. It's called an affinity pool that's going to look at locality in terms of CPU cores. So just to be aware a bit of how this is all working. So if you're using actors and you have mutable state, which I do hope, because that's the big advantage of using actors, is the moment that you want to share things, use immutable messages. In Scala, that's easy. Just use a case class, and by default, that's going to give you something. Just use immutable data structures in the messages that you're defining. And in Java, you can use libraries like I think immutables, or there's a few libraries that you can use that are going to generate all of this for you. If you want to ask an actor, hey, what's your current state? You can use queries. We're going to look at the ask pattern for that, or you can, the other way around, which is actually the better way, is the actor just should emit their state using events to others, and then anyone else can react to that. And then for asynchronous calls, use the, which is to say, when you use futures inside of an actor, use the pipe pattern. So in practice, how does that look? For example, here we are going to want to retrieve a document from someplace else. Okay, so we got a document ID, and then the first thing we're doing is we compute a URL out of this. And what's pretty important in distributed systems is you always want to use boundaries in time. You don't want to let your users waiting for 10 minutes if the remote system, for one reason or another, is not going to reply in time. So here I've set a 5 seconds boundary to get back this document. I'm asking now, with this question mark here, means ask. I'm asking the file fetcher to retrieve the document at that location. And then in case this future is failing, I'm adding a failure handler here on the result with a ask timeout exception. If that's failing, I'm transforming this into a file fetch failure with the context, with my document ID. If I didn't do that, I would lose the context. I wouldn't know anymore later on what is the fetching, what did fail here. And then you can see at the end of this, I'm doing result pipe to self. What that means is when the result future is going to be completed, it's going to send a message to another actor, or in this case, to myself. I pass an actor reference there, so I'm saying here, when this is done, when this future is done, send this as a message, and now we're back in the message passing paradigm of Akka. And then there is two more cases that I need to handle here. Either I'm lucky and my fetch has succeeded, I'm getting the data, I can do what I want with it, or the fetch has failed, and then life is not good. But then still, because I captured the context earlier on, I have a document ID that I can use in order to recover or do something. So it's important to keep this context, okay? Otherwise, you're just getting an exception or a failure and you don't know what has failed. So that's also very important, is when you're working with actors, design little protocols inside of these actors just to capture context. Okay, now that was the first one. Let's move to the second one. The two enemies of human happiness are pain and boredom. You know, the quotes are not going to get much brighter during this talk. This is just going to go down the hill. So that was Arthur Schopenhauer. Second anti-pattern is about flat actor hierarchies. And that's, you know, that's this flat, nice ocean, where you would think that's nice, right? But the thing is, we're working with distributed systems. And, you know, as from the keynote on 2 days ago, this is how it looks like, right? You don't have a flat ocean. You have it's like, it's not nice out there. I mean, it's not nice. Some people really like this. But that's the reality. We're working in a real world. Networks are inherently unstable. They're failing all the time. So the actor model gives us this opportunity to work with failure in a way that's going to be much easier to reason about and think about and anticipate than in a, let's say, traditional way with checked exceptions. So this here would be a flat hierarchy. Ceci n'est pas une hiérarchie. That was a painting from Magritte, if you know that Belgian surrealist. Anyway, so what you have here is the root level, top level actor, the guardian, then you have the user, space guardian, and you have 3 top level actors. That's not a hierarchy. That's just a one flat set of 3 actors. And why is that bad? Well, the thing is that if you don't have an hierarchy in your actor system, unless you have a really simple hello world example, you're missing the point. Because the point of actor systems is not only to provide concurrencies, not only to let you scale out, but also to, and foremost in my view, that's one of the nicest things about the Reactive Manifesto is the failure tolerance part. So, and the way actors and the actor model defines failure handling is through the hierarchy itself. So you have an actor, and that actor has child actors. If a child actor fails, it's going to be their parent that's going to be responsible for taking action and deciding what's going to happen. Is that actor going to be restored? Is it going to be stopped? What are we going to do? So if you don't have a hierarchy, you don't have failure handling. And then, you know, you might as well not use actors in the first place. In fact, yeah, we'll circle back to checked exceptions here. So this is what happens. There was a study a few years ago, is looking at a lot of lines of Java code. What's happening in the catch statement? Well, the foremost thing that people are doing, it's quite logging that there was an exception. Okay, now we logged it. But yeah, so someone can figure it out. At least it's logged. The second one is print stack trace. So it's a little bit less elegant than the logging, but at least it's gonna hopefully appear somewhere. So in case the system crashes, we might have a chance to know what's going on. The third one is a bit sociopathic. It's if you really don't like the other people you're working with, you're going to suppress the stack trace and the fact that it was an exception in the first place, which is to say that if the system for some reason or another fails at 3 in the morning, nobody knows why, because there is no stack trace. Yeah. And then we see the cases where we start throwing things in a more controlled way, we rethrow, and we start dealing with the failure, okay? But that's like coming on the fourth place, it's much less frequent. And that is to say that using this approach of checked exception doesn't actually yield code or systems that are going to tend towards reacting to failure and being able to sort of self-heal. And that is where the actor model lets us do this. So Joe Armstrong, who built the Ericsson language, the Erlang language at Ericsson, was sort of after which Akka has been modeled, says that repeat after me, errors should be handled out of a band in a parallel process. They're not part of the main application. And that is to say, you have your application, your happy path, you're doing things, calling things, but then if something fails, that is going to be dealt with at another level. That's going to be the supervisor. So in case of actors, what happens is if the actor crashes, so if inside of an actor an exception is thrown, the actor crashes and it's the supervisor who is up to the task, who has to decide what to do. And in that way, we can decide, we have a built-in mechanism for recovery. So the default thing that Akka does is if your actor crashes, it will restart the actor will lose its internal state, and then it starts again and can continue processing. This is just one of 4 ways in which a supervisor can deal with the failure of an actor. And this is, I think, it's one of the most important things if you're designing actor systems, is do think about how this thing is going to fail, who needs to supervise what, and what happens if an actor goes away, if their state goes away. This is really important. This is like key to building resilient systems. Third anti-pattern, the mother of excess is not joy, but joylessness, from Friedrich Nietzsche. That's anti-pattern number 3. Too many actor systems. So granted, I haven't seen this very often, this one, but I've seen it a few times too many, so it's on the slide deck as well here. And what can happen, what I've seen, the most extreme case is I had like one JVM, 140 actor systems. A lot of memory, but 140 actor systems. So initially the intent was good because what they wanted to achieve here was to isolate one thing from another. Isolation is good, right? But then creating one actor system per container or per thing is not the answer to that. Because Akka actually has all what you need to do that in Akka itself. So the reason why you shouldn't have all these actor systems in one JVM is, well, each actor system is backed by one thread pool, and these things are heavy. They need memory. They need resources. When they're working, they're going to start contending for resources. And then you could have the nicest 4-join dispatcher of the world. It wouldn't help if you have 440 of them running side by side. It's still going to be very painful to watch. So how to do this? This is simple. Just trust Akka to do the right thing. Use what Akka has defined. And we said this tool is called dispatchers. So the dispatcher, we looked at it before, is this thing that is deciding what is going to be running in what order. You can define custom dispatchers. So you can define bulkheading. You probably saw this before, like bulkheads unlike on the Titanic. You know, the Titanic also had bulkheads, but they were open on top. So it was more of a design thing to have bulkheads there. They didn't really help. The thing just went down anyway. So if you have bulkheads, they need to be closed, otherwise they're not serving a purpose. So here is how that would look like. You would define in configuration, like for example, a thread pool executor that has a fixed pool size of 2 for your graph database, and then when you're creating the actor that interacts with the graph database, you would limit that amount of threads that this thing can talk to by configuring this custom dispatcher. And then you sort of have this, you can be sure that it's not going to take over your world. Like if your graph database is blocking for one reason, if the calls to that are blocking, you can't just take over the world and have everything being blocked just because of that one dispatcher, this one blocking code. So, fourth anti-pattern, I think. Words, words, words. That's from William Shakespeare's Hamlet. And this is a bit less about Akka, also Akka, of course. Important in the context of Akka, but this is the number one reason for low performance in systems. It's logging. Who would have thought, right? So I think we saw it this morning, and Verizon said that one of the strategies for staying up when there was a lot of traffic was to disable logging. Well, yeah, logging is expensive, especially if it's configured in such a way that the logging itself is blocking. So what are the things that can happen that are not ideal? Is if you're developing an application, you probably have debug logs, okay? And then if you're using string concatenation with a call to the toString method, that is expensive. So the worst case I've seen is when there was a toString method on like a data object, and it turns out that toString was calling the database and pulling out context out of the database to render the object. And that's nice because suddenly your system goes down in flames and, and the DBAs come and yell at you. So that is one thing. So if you use string concatenation in the debug statements, that's gonna come back and bite you. Non-asynchronous logging, that's a configuration problem really. Is if you're not using asynchronous appenders and writing synchronously to the file system, you're limiting the throughput of your system to the write to the disk I/O write throughput of the system, and there's no reason for that coupling. I've also seen like not turning debug logging off in production settings when you're deploying to production. You don't necessarily want to debug everything. And then logging to files, really, that's not what you should be doing anyway anymore. It's like go to something like Elastic or else just to aggregate logs and go through them. So in terms of why is this really relevant with Akka, well, Akka, usually you want to do a lot with it. So you want to process like millions of messages per second, or maybe a bit less, but still you wanna like the big systems, they're going to potentially process a lot of transactions, and that is one of the things to get right, because if you get it wrong, it can really come back at you, and that's, yeah. So what to do instead? Well, first of all, there is a logging facility in Akka. Just use that. Don't pull in something else. You don't need to pull in something else, just use that. Make sure you configure like the logging backend that's logged back by default. You can use the asynchronous variants. There is also a log4j2 adapter. Log4j2 is orders of magnitude faster than logback, actually. That's a nice thing, but there is also an adapter that you can use for that. And then if you're using debug logging, always use this syntax where you're using a placeholder, like this empty curly braces, because what that means is that the message.toString will only be called when you actually want to print this, and not beforehand, because otherwise the compiler will just go and call your database when it's, yeah. Use logstash, use aggregations, and just be careful in general about logging. It's a trap. It's something that can go wrong easily. Now, this is one of my favorites. All that we see or seem is but a dream within a dream. That's by Edgar Allan Poe. Very nice poem. And that brings us to our fifth anti-pattern. Being out of touch with the hardware. And I think, especially now, 2017, 2016, but especially 2017 is the year of doing this. So this is the year of Docker. So first of all, who is running their system with virtual machines, where there is virtual machines involved? If you're using AWS or any cloud service like ECS, you have to say yes, because there's going to be a virtual machine there. Now, who is using Docker? Yeah, a lot of people. Who is using JVMs inside of Docker? Yeah, so we're at third level of abstraction. Who is using Akka and the JVM in Docker on the virtual machine on your server? Yeah. So what I'm trying to get at is, I really like this quote by Martin Thompson. Hardware tries so hard to make software fast. Software tries so hard to make hardware slow. This is this is really something that I see a lot, and usually when you're using Akka, you have some type of interest in the system being performant, right? It's going to be one of your concerns. Is why you're using Akka? Well, you want things to be concurrent, you want to be fast, and by using all of these things, what happens at the end of the day is you can be really slow, because Akka and the default fork join dispatcher executor service needs to know how many threads it should have, so you configure something, and the optimal amount of threads that you need for your system is going to depend on the available processors times a scaling factor. Now the thing is, if you're running this inside of a virtual machine, inside of Docker, inside of what's or not, so you don't necessarily know what is the right amount of processors to put there, because first of all, well, you're going to share the CPU across many containers, across many things, and then second of all, yeah, it's hard to figure out what's the right amount of cores to put there. And if you don't have the right amount of threads for your system, you will have to pay the price of context switching. And that's just the CPU. I'm not even talking about the network. You're also contending for the network, so you better make sure that you have a really fast network on these things. So what to do instead here? Know that, get some knowledge or get a sense of what you're running on, and make sure you know what, like, some hypervisors are really bad, right? They lie to you. So you think you have 4 cores, but really it's only 2 cores, but they made it just virtual cores because that sounded better, and you end up overshooting the amount of threads you need and making it all worse. Also, one thing I've seen is if you're running load tests, make sure you run them on the same hardware then your production system will run, because if you don't have the same, then your load test doesn't mean anything, right? So if you have a staging environment for load tests, make sure it's the same configuration exactly. Otherwise, your load test is a bit useless. Okay, next is a bit of a longer slide here. Some men aren't looking for anything logical, like money. They can't be bought, bullied, reasoned, or negotiated with. Some men just want to watch the world burn. That's from Alfred in Batman: The Dark Knight, brilliant movie. Our 6th anti-pattern is blocking. I think everyone is aware of that. That's not the nicest thing to do. So how can that happen? Well, you could be calling a synchronous API, a legacy API, and that's blocking and that's bad. But we all know that. That's okay. The subtle thing here is you could be calling an asynchronous API that's calling another asynchronous API, and then somewhere down the line, it's calling a synchronous API, but you don't know that because you didn't write that code. There was a bug in one of the latest Play releases. It's fixed now, where it was using a library that was at some point blocking, and then boom, that was having an impact on systems. This is a subtle thing, is how do you know that somewhere down the line you're using blocking? There is a project called Reactive Audit out there. I will make sure to put that on Twitter, is that it is looking through your code, instrumenting your code, and looking what it's calling in terms of JVM, native JVM APIs. And if one of them is blocking, it's going to tell you what it is. What I've also seen is, especially if you're new to all this asynchronous thinking, is it's a nice shortcut to just wait explicitly for the completion of a future. How bad can it be? I put this here, I wait for 2 seconds, but then suddenly I have 1,000 concurrent users and the thing goes down in flames. So that's one thing that also don't block. Just don't block. This is what happens if you're blocking. If we look at this is like CPU cycles, like the simple register to register operations, really cheap. And then down the line, down there, like this is the last line, which is between 10,000 and 1 million CPU cycles. That's when you context switch with the full cache invalidation and so on. So every time your operating system has to switch out the thread, it's really expensive, and that's really a problem when you're trying to build a high-performance system. And there's a nice scale down there for comparison. Like this is really, really expensive. It's not something to joke about. I just spent the last 3 months optimizing a Vadin application, which is which was not using the Servlet 3 asynchronous API, but the Servlet 2 blocking API. It's really hard to scale these things. So if you really have to, if you can't do it otherwise, you have to block. Use a dedicated dispatcher, the one we talked about earlier on, where you sort of limit it in terms of the harm it can do to the rest of your system. And if you're doing something where you need to wait for like some time, rather than just doing a thread sleep or something like this, use a scheduler to call you back and go back in the message passing paradigm for all these routine tasks, which are time-bound in one way or another, or use the ask pattern. All right, so next anti-pattern. The desire of excessive power caused the angels to fall. I was telling Francis Bacon, this is not getting any better. So what is this one about? It's about using Akka remoting, at least directly, okay? So, and that's one thing unfortunately I've seen a few times, is people start building things and they see Akka remoting. So Akka remoting is the module of Akka that lets you deploy actors on another machine, okay? So that's nice and all, now you have the network. But then, unless you're this guy, you don't want to do that, because it's all about the fine print at the end of the day. So this is the life cycle of a system with Akka remoting, and you have to read the fine print. So what does the fine print says is that remote system must be restarted to be able to establish a communication again. So in case your network fails, and it will, you're going to have to restart the other side, explicitly restart the other side to make sure the system is whole again. So if you only have two parties, okay, maybe that's not too bad, you can sort of solve that. But the moment you want to build something with more than two nodes, it's going to be something. So what do you have to do? Well, like the third rule of the Distributed Systems Club is don't trust the network. Okay, your network will be failing. So what that means is you need to detect that the network will be failing, so you have to implement a failure detector. And then once you have detected failure, you have to make sure that you're going to recover from failure. And then if you want to have more than two nodes, you have to start spreading information as to the state of different nodes, and that you can do. You can implement a gossip protocol. And I've seen all of that. I've seen people build their own failure detectors, build a gossip protocol, more or less performant gossip protocol. But don't do that, because there is Akka cluster, which happens to implement a failure detector, and also a nice gossip protocol that's based on Amazon Dynamo, I think, and Redis. Is it Redis? No, it was, well, one of the key value stores. And so it's really working, this thing. So what is Akka Cluster? Akka Cluster is a membership service. It's something that tells you who is there in the cluster, who is there, who may not be there at the moment, who we haven't been able to reach for some time, who can we trust, who can we not trust. It's based around the fee accrual failure detector. So it's not just saying, oh, I didn't see this guy respond to my ping, I'm going offline. It's looking at the history of what has happened, the pings at the round trip times, and if there is a sudden deviation, it can give you a sense of what's going on. So it was not Redis, it was Reactive. Okay, that was the gossip protocol. So this is really working. This is scaling to like many nodes. You can, I think, like up to 2,400 was an experiment, maybe more at the moment. So there, you can even build a lot of big clusters with that. So one thing though is that you're still on the network, okay? Even if you use Akka Cluster, it's no silver bullet. It's no magic thing that you spray and then suddenly everything becomes nice and such. So there will still be network partitions, especially if you're using cloud environments. So I've run an experiment a few months ago where I had like 400 node cluster on AWS, and what happens is not so much that the entire cluster gets partitioned in two, but more like individual nodes will just disappear, okay? and then they come back 5 minutes later and they wonder what has happened. So you will have network partitions. It's a fact of life. Sorry, there is no way around. So make sure you have a split brain resolver in place, and also, if you're deploying this in a cloud environment and not on hardware, make sure you know the failure detector you're using, because if you're using the default settings, it may not be optimal for use in your cloud environment. So I wrote a little thing on that if you're interested on the topic of failure detectors. And in terms of split brain resolvers, I think the only real alternative is the Lightband split brain resolver that works really well. I haven't seen anything that's production quality out there. And Lightband is not paying me for saying that. This is what I also recommend to my clients. It's just use that, it's working. It's also very easy to think that you wrote a split brain resolver that works, and it doesn't. So there's a few open source versions of it out there. None of them is right. So they're all wrong. It's all experimental. So I wouldn't recommend that for production use. Right. So that was about the network. So now to finish with a nice quote here. This is the way the world ends, not with a bang, but with a whimper, by T.S. Eliot. The 8th anti-pattern using Java serialization. You may notice the 4 angels of the apocalypse in the background. I think that's quite appropriate because, and I have seen that is that if you use this and you launch in production, and you build a system that can't be like that, you don't have the luxury of turning off to do an update. I mean, you built it because you want it to be always on, right? So with a high SLA and so on. If you can turn it off, but you have used like Java serialization, you're in a very, very poor position. So what happens is it's on by default. I think it's still on by default. I'm not sure. But there is a warning, so it's warning you that, hey, don't use this in production, but then people tend to ignore that and use it anyway. What can happen? There's 2 things. First of all, Java serialization over the wire is tremendously bad. It's just not fast. And then if you're using Akka persistence, Java serialization, the moment you're going to evolve your protocol, your schema, it's not designed for that. It's not gonna work very well. Actually, it's going to throw an exception, I think. So there is adapters in Akka now for dealing with versions, but then again, if you're using Java serialization, it's not going to be very funny to do that. So don't use Java serialization. Yeah, you pay the penalty in terms of performance, protocol evolution. It's not designed for it. It's not meant for that. It's not meant for anything, really. So just don't use it. So what to do instead is, the first thing, if you know that you're going to either use cluster or use Akka persistence, the first thing is you have to decide on a binary format. So there's quite a few alternatives, protobuf, Avro, or Thrift. I tend to like Avro for anything that's going to be used for inter-process communication, like in a microservice environment. Also because there is a schema, there is already a schema library or schema management library that interacts with Kafka for Avro. So that actually goes to publish your new versions of a schema through Kafka itself, through a topic in Kafka. So your services get the new version and they can react accordingly. Granted, that is something that will be more relevant maybe in larger systems where you have large teams, where you have many people. But then again, this is the sort of system that are the hardest to get right. And yeah, once you're in production, it's sort of too late for doing changes there. It's hard to do changes without sort of at least having some sort of downtime. So make that decision early. Yeah. I think that's pretty much all I had for now. And so I think we should have some time for questions. Yep. OK, that's good. So if there's any questions, yeah, we do have some time.
Manuel, you mentioned about how, for you, the year 2017 was the year of the Akka cluster. And I got to thinking maybe you had some war stories in mind, and you did share some, but was there something in particular that you would like to elaborate on? By the way, great talk.
Thanks. A particular war story with Akka cluster this year. And it was last year. I had a very interesting one where, with this Java serialization, seeing Java serialization and just looking away because it's. This year, though, is. So what I've done this year mostly is training teams in terms of using it. Oh yeah, one team, but that was crisis averted. Is they got the training with where also remoting is being mentioned. It's part of the training, but I kind of only mention it and move to cluster. But they started building their own cluster on top of remoting again. I don't know why people tend to do that, so that was not really one thing where we were in the trenches for a month and trying to recover it, fortunately. Yeah, it's. So the worst damage I've seen in terms of damage, I mean, orders of a few $1 million of lost money, actual cash, is because of Java serialization. So, yeah. That is not, don't underestimate the power of that.
So you mentioned blocking. Are there any good patterns for, say, the transmission of back pressure within Akka? I know we've seen streams and all of that stuff, but are there any other patterns that you can elaborate on?
So other than reactive streams for non-blocking back pressure, that's, well, I mean, what we did before we had reactive streams was to use control messages that sort of flow back. And then you may have to make sure that you're separating your control flow messages from the other messages. So for this, you're using different mailbox type. So there is a property called control-aware mailbox, which is to say that if you have a message that's a control message, it's going to be processed first before the business messages. So that if you are in a situation where you need to do this low-level work on your own and you, for one reason or another, cannot use Akka streams, then that is what I would recommend. Just use this other type of mailbox.
Hi, thanks for this talk, very interesting. About one of the patterns was about using the pipe2 pattern.
Yep.
I've used that and seen in many examples when you have to pipe results to the sender.
Yep.
But in your example, you were piping to yourself. And so I'm wondering, in that case, what would be wrong with a simple tell?
With a tell. Well, what pipe does is it takes a future, okay? So a future, well, it's more like, in this case, it would be a syntactic error, but what happens is the future will complete, and either it will fail or it will succeed. And what pipe does really is taking the completed result and sending that as a message. So it's really a shortcut for doing this incomplete work in case of a future. Now, you mentioned, say, piping back to the sender. So just one thing is, that is one thing you can use indeed, because one trap is to close over the sender in asynchronous calls, and by the time your callback comes back, it's a different sender. So be careful about that as well. You're closing over mutable state sender is mutable in that thing. So you capture the sender before you do asynchronous calls. Other than that, that's one thing, often seeing that as well.
You mentioned that understanding your hardware is very necessary because of the way Akka interacts with threads, and that 2017 is kind of the year of getting away from that with Docker and Kubernetes and so forth. However, one of the trade-offs is that with Docker, you can include explicitly all of your dependencies and you don't necessarily have to worry about what's on your target system. Is there a way that we can still get that benefit out of Docker and mitigate the problem of not necessarily knowing about the thread pools on your hardware?
Well, yeah. So I think if you understand you right, is how can you make sure you're going to use Docker and Akka in combination in an optimal way, right? So, if I'm not mistaken, I'm not sure if in Docker, depending on where you deploy it on, you can say I want 4 cores or I want this, And if you have an environment that you trust, where it's actually going to be real cores and not shared or virtualized cores, you're going to be in a good situation. I think on Amazon ECS, you say, I want 1024 is going to be 2 cores. No, it's going to be 1 core. So you say a number. So you sort of translate this to sort of virtual CPU units. And that maps pretty well by now, I think. But you need to know what it is. And then you need to know how many you have and use that number. So say you have 4. You want to use that in your configuration and say, I have 2 times 4, which is to say 8. But that's just an indication. It's a good first guess, because the number of threads you need is going to be a function of how your actor system works. So what the fork join, at least if you're using the fork join dispatcher, is what it's going to do is going to try to keep everyone really, really busy. But your actor system will not have actors that are going to be completely homogeneous. You will have actors that will be very busy and actors that are not going to do a lot of things. And depending on how your actor system is designed, you need to sort of adjust that a little bit. And that sort of work, that is experimentation. You need to just run load tests and then tweak a little bit, and you get a better sense of how the system performs under load. So load tests is, I think, a very important key point here. Is if you're interested in building a really high-performance system, have something automated, use, what's it called, Gatling for that, or a tool of the kind to really get a sense of the performance profile of your application.
So I'm new to Akka. What use cases, now that there's Akka Streams and Akka HDP and Play, which use cases would I still use actors for?
Okay, so where would you only want to use simple actors and not use any of the high-level abstractions? Honestly, I find, but then maybe I'm old school, but I find it when I have a simple when I have a simple system where I need a bit of concurrency, a bit of interaction, and it's not too many of them. I like to use the actor model because it's easy to reason about, and you can reason about in terms of business of what's happening with events. You can really easily reason about that. Now, if you have Reactive Streams, is a very powerful tool. There is a learning curve with Akka Streams as well. There are a lot of combinators, and that's more for stream processing, I would say, than simple state. And simple durable state. But then what I would recommend is, even if it's still experimental, look into Akka Typed. So that is the project that is about typing, making typed actors, because that removes one of these things where everyone does that when they start, they send the message to the wrong actor, or they send the wrong message to the right actor. And then the logging is not configured properly, and the messages get lost, and nothing happens, and you wonder why. And Akka Typed is exactly about that. It's catching this, making sure the protocol is captured by the compiler. So look at that project. I think that's what a lot will be built upon in the future. Yep.
So a follow-up question to that. A choice between using futures and actors, why would I just not use futures?
So that is a very good question. Futures are for short-term asynchronous computation. One-shot things, like I'm calling a web service, here's the result. There I have it. And my state is just this one thing, this one result. So that's a very short-term thing. But then when you have state that has a longer duration than just this one-shot thing, that's where you use actors. When you have model users, that's going to be a user session is going to be something that's more long-lived in your system than your future. I've seen approaches where people try to do everything with futures. The problem with that is that the futures don't give you a good failure recovery mechanism. The moment you start composing them, it's you game over, because okay, your failure will propagate to the end, but then all of your chain is done. You have done it once, and that's it. There is no way to recover. Actors, you get the supervisor actor that's going to be taking care of your failure and recovering from that, and that's how you build a resilient system. Futures are just this one-shot thing. So yeah, the rule is simply, if you do a thing that works only once, it's just use futures, and if you have something that's more long-lasting, use actors. That's what I would say.
So I had a question. In Akka, the dispatcher is really about processing the mailboxes, but let's say you have a lot of asynchronous work you're doing in addition to in futures, and you're piping those results correctly and all that stuff. Do you have any guidance or thoughts on using separate, I guess, execution contexts for cases where you have a lot of that asynchronous work, or is using the dispatcher given to you by your actor system usually always kind of the best approach there?
So yeah, if I understand you right, do we always use the same one? If we're completely asynchronous, do we use the same thing, the same actor, like dispatcher, or do we use several ones? Oh, asynchronous. So if you have asynchronous calls, I mean, what's very convenient is just reuse the same dispatcher, use the same thing, except that I guess that also depends on your application. I mean, if you have parts of your actor tree that are really important, like your billing system, or I don't know, like really core things, like you can use bulkheading and custom dispatchers to make sure that this part will always have the resources it needs. If you have things that have to absolutely be able to work, you can even use things like pin dispatchers to pin a thread to the actor and make sure that it's going to be always, with all the trade-offs, of course. But it's going to be, there is no global answer to that. That's very dependent on the system that you're having. Yeah. Okay, I think we're out of time. Thank you very much. So I'm blogging about this. So all of these anti-patterns, these are 8 out of, I don't even know, 15 by now. On my blog, there is a list of them all, so you can go and collect them and read about all of that. And yeah, don't hesitate to contact me like now, or also on Twitter or per email. Just yeah, thank you.